In the vast expanse of space surrounding our planet, a crisis is brewing. Imagine a scenario where humanity becomes trapped on Earth, unable to launch satellites or spacecraft because our own space debris has created an impenetrable barrier around our planet. This isn't science fiction. It's a real possibility known as the Kessler Syndrome, first predicted by NASA scientist Donald J. Kessler in 1978. But what led this visionary scientist to propose such a devastating theory? And more importantly, how close are we to this point of no return? Back in 1978, Donald Kessler wasn't just making wild predictions. His concerns arose from careful observation of the rapidly growing population of man-made objects in Earth's orbit during the space race era. Using data from the North American Aerospace Defense Command, NORAD, Kessler made a startling discovery. 42% of all catalogued debris originated from just 19 events, primarily explosions of spent rocket stages. This revelation led him to develop mathematical models showing how collisions in low Earth orbit could create a catastrophic cascade effect, much like studying asteroid belts, but with consequences unfolding over decades rather than billions of years. At its core, the Kessler Syndrome represents a devastating chain reaction in space, where collisions between satellites and debris create more debris, which causes more collisions, creating even more debris. But what makes this scenario particularly frightening is the physics behind it. Objects in low Earth orbit travel at staggering speeds of up to 22,000 kilometers per hour. At these velocities, even a fragment weighing just 1 kilogram traveling at 10 kilometers per second can completely destroy a 1,000 kilogram satellite. This single collision can generate thousands of new fragments, each becoming a potential projectile in this deadly orbital dance. Think of it like a game of cosmic billiards, but where each collision creates dozens of new balls, all moving at hypersonic speeds. The process becomes self-sustaining once the density of objects reaches a critical threshold, a point where the rate of debris generation exceeds the natural decay caused by atmospheric drag. As of 2024, the situation in Earth's orbit is already precarious. Over 47,000 objects larger than 10 centimeters are currently being tracked in orbit. But here's what keeps space experts awake at night. This represents only 1% of the total debris population. Current estimates suggest there are approximately 900,000 pieces between 1 and 10 centimeters in size, and an astounding 128 million pieces smaller than 1 centimeter. Let's put this in perspective. Even a paint fleck traveling at orbital speeds can puncture a spacesuit or damage crucial satellite components. The region between 800 and 900 kilometers above Earth has become particularly hazardous, earning the ominous nickname, the bad neighborhood. Nearly 1/3 of the most dangerous orbital conjunctions, or close approaches, occur in this region. What's particularly concerning is the rapid proliferation of nanosatellites. While these small satellites can help with debris monitoring and removal, their sheer numbers pose new challenges. By 2030, experts project over 100,000 new spacecraft could be launched into orbit, many of them nanosatellites. Their small size makes them harder to track, and some older designs lack proper propulsion systems for collision avoidance. The challenge of space debris has sparked unprecedented international collaboration, though the regulatory framework remains a work in progress. The foundation of space law, the 1967 Outer Space Treaty, established space as a global commons and requires nations to avoid harmful contamination of the orbital environment. The 1972 Liability Convention added crucial accountability, making nations legally responsible for damage caused by their space objects, including debris. The 2007 UN Space Debris Mitigation Guidelines later established best practices like limiting debris release during operations, preventing breakups through fuel venting, and ensuring satellites deorbit within 25 years after their mission ends. However, these guidelines remain voluntary, leading to inconsistent implementation across nations. We've already witnessed several alarming incidents that showcase the potential for a catastrophic cascade. The 2009 collision between an American Iridium satellite and a defunct Russian Cosmos 2251 satellite created over 2,000 pieces of trackable debris. More recently, in August 2024, a Chinese Long March 6A rocket broke apart in orbit, adding hundreds more fragments to the growing cloud of space junk. These aren't isolated incidents. The threat continues to grow with each launch and deliberate action. Anti-satellite (ASAT) tests have been particularly devastating. The 2021 Russian ASAT test generated over 1,500 trackable fragments, forcing International Space Station crew members to shelter in escape vehicles. Consider the Cluster 850, a group of 36 massive derelict objects, weighing approximately 208,000 kilograms, concentrated in an orbital band between 825 and 865 kilometers. Experts estimate there's a 1 in 580 chance per year of a collision within this cluster alone. If such a collision occurs, it could generate over 15,000 trackable fragments, merely doubling the current debris population in low Earth orbit from a single event. The implications of the Kessler Syndrome extend far beyond the realm of space exploration. Our modern civilization relies heavily on satellite infrastructure. Global communications, weather forecasting, GPS navigation, climate monitoring, and disaster response systems would all be severely compromised or completely disabled. The economic impact would be staggering. The OECD estimates potential monetary losses from Kessler Syndrome at $191.3 billion. The impact on space operations is already evident. Satellite operators must perform increasingly frequent collision avoidance maneuvers, consuming precious fuel and reducing satellite lifespans. The proliferation of debris has led to higher operational costs due to enhanced tracking requirements and increased insurance premiums. Developing nations face particular challenges as the growing risks and costs make it increasingly difficult to access space and maintain crucial satellite infrastructure. But the consequences don't stop there. Rural areas and developing nations that rely heavily on satellite-based infrastructure would face disproportionate impacts. Military operations would be hindered, potentially destabilizing global security. Even our ability to monitor and respond to climate change would be severely impacted, as we'd lose access to crucial environmental monitoring satellites. The story becomes even more complex when we consider how natural phenomena influence the debris environment. Solar flares and geomagnetic storms can cause the Earth's atmosphere to expand, increasing drag on orbital objects. While this can help clear debris at lower altitudes, it also creates unpredictable conditions that can increase collision risks. For instance, in February 2022, a mild geomagnetic storm caused SpaceX to lose 40 newly launched Starlink satellites due to unexpected atmospheric drag. Despite this grim scenario, scientists and engineers aren't sitting idle. Innovative solutions are being developed to address the crisis. The European Space Agency's Clear Space 1 mission plans to use robotic arms to remove defunct satellites. Technologies like laser ablation, which uses high-powered lasers to nudge debris into lower orbits, show promise for dealing with smaller fragments. The Remove Debris mission has successfully demonstrated net capture technology by capturing a CubeSat in orbit. Meanwhile, private companies are joining the cleanup effort. SpaceX is exploring space tug concepts to remove large debris pieces, showing how commercial space companies are beginning to take responsibility for orbital sustainability. Space agencies are also implementing stricter guidelines. The traditional 25-year rule for post-mission satellite disposal is being shortened to just 5 years. Current compliance rates with debris mitigation guidelines vary widely, from 45% to 90% depending on orbital region. However, when naturally compliant objects are excluded, actual compliance drops to as low as 10 to 40% for non-naturally decaying satellites. Some nations are taking stronger action. The European Space Agency's Zero Debris approach aims to eliminate new debris generation by 2030. Organizations like the Interagency Space Debris Coordination Committee, IADC, are working to harmonize standards and encourage responsible behavior among space actors. However, the voluntary nature of these guidelines remains a significant challenge, as there are no penalties for non-compliance. As we stand at this crucial juncture in human spaceflight, the urgency couldn't be clearer. Models suggest that even without new launches, collisions among existing debris could become self-sustaining within a few decades. Some orbital regions could reach critical density thresholds as early as the mid-21st century. The window for action is closing, but it hasn't closed yet. Will we heed these warning signs and protect our access to space, or will we allow our orbital highways to become an impassable junkyard? Understanding and addressing the Kessler Syndrome isn't just about preserving our satellite infrastructure or maintaining our ability to explore space. It's about ensuring that future generations inherit a cosmos that remains accessible and full of possibilities rather than an orbital wasteland of our own making.